In this video I will go over the homework that follows the lecture 9.2 that focuses on integrating the powers of secant and tangent. So as always, I hope you watched these lectures, as I will be making references and assuming that you have a basic understanding of the material presented in them. In these lectures, we learn how to integrate the powers of secant, the powers of tangent, and the products of powers of secant and tangent. So let's go ahead and start the homework. And right away, we have a problem in which we have a product of powers. As always, we're going to do some basic hygiene here, and we're going to replace, this time I'm just going to use the letter theta. And replace pi x with theta. So d theta will be pi dx. Therefore, dx will be 1 over pi d theta. And my original integral now becomes, I take out negative 2 pi, and then when I replace dx with 1 over pi d theta, 1 over pi can also come out. And what we have inside is just the tangent to the power 5 of theta times secant to the power 3 of theta d theta. Now, to integrate this type of product, let's go back over here and review this lecture real quick. In this lecture, let's just jump right over here. This will give us everything we need to know. Right over here. So I'm going to maximize it real quick, just so we can see it. What matters here is the whether the powers are even or odd. So in our case, we have odd, both are odd. So if they both are odd, then which of these three cases applies? Well, if they're both odd, that means n is not even. If they both odd, that means m is not even. So if they're both odd, that means even though they are both odd, there's nothing we can do with an odd power of secant. But when the odd power of tangent is there, we can use the split and substitute technique by splitting away both secant and tangent. That's the idea. So, and that's exactly what we're going to do. We're going to split and substitute. So the first step is to split. I'm going to pull off a tangent and secant. So we have now tangent, theta, secant, theta, d theta. And I'm going to do this substitution. So my substitution will be s is equal to secant theta. So that means ds is equal to tangent theta secant theta, and now I need to replace the tangent to the power 4 as the square of tangent squared, because I can replace then, using the Pythagorean identity, tangent squared of theta with s squared minus 1. So let's implement this substitution. So we have an integral of s squared minus 1 squared times s squared times ds. And this is a simple integral. It's just negative 2. We have s to the power 4 multiplied by s squared is s to the 6. So what I'm doing right now, I'm just distributing everything and writing this polynomial in standard form, minus 2s squared, so it becomes 2s to the 4 plus 1, which is s squared ds. Now the answer is negative 217 s to the 7 minus 2/5 s to the 5th plus 1/3 s to the 3rd. But remember what s is. S is secant theta. So we have 1/7 secant to the power 7 of theta, but what's theta? Theta is pi x. So the final answer is obtained after replacing all the new variables with what they stand for in terms of x. And this is the final answer. So let's go ahead and enter it. And of course we got it right. There's no reason for us to get it wrong. Let's check what they have done. And they have done the same thing, except they skipped the first step of substituting pi x. I think it's better that way. You really clean up your integral right away, avoiding writing all those pi x's throughout the entire solution. So let's move on to the next question. We have number 2, integral of 4 times tangent to the power 5 of 5x dx. So now we have powers of tangent only. Before I look up the methods for integrating powers of tangent, I'm going to do some basic cleaning here. I'm going to do a substitution. 5x is equal to theta, so 5 dx is equal to d theta, meaning dx is equal to 1/5 d theta. And now we take out 4, and also 1/5 comes outside, and we have tangent to the power of 5 of theta d theta. And how do we integrate powers of tangent? This is what we discussed in this video. Just to go real quick here, we definitely should know all this for powers up to 4, and since we have power of 5, we probably need to learn this approach. And in this approach, we're given a recursive formula. But if you don't want to use recursive formula, then you just have to follow this trig identity method described in this video. I'm going to use the recursive formula just because it's that good, and I don't see a reason why wouldn't I want to use it here. So the tangent to the power 5, but as I'm using it, let me, I guess, put it over here for the reference. So the substitution, the recursive formula that I'm using is right here. Integral of tangent to the power n of x dx is equal to 1 over n minus 1 tangent to the power n minus 1 x minus integral of tangent n minus 2 x dx. Meaning when n is equal to 5, here's what I get. I'm going to get 1 over 4 tangent to the power 4x minus integral of tangent to the power 3. But tangent to the power 3 can be done in using exactly the same formula. So instead of tangent to the power 3, I'm going to plug in here the result of using the recursive formula. So it's going to be 1 over 2 tangent squared x minus integral of just tangent x dx. But we know exactly what the integral of tangent x dx is because it's one of the basic results. So the final answer will be 4/5 1/4 tangent to the power 4 x minus 1/2. I'm just going to distribute some of the negatives to get rid of the parentheses. And now we're writing this integral of tangent x with the plus sign. And integral of tangent x, it's ln of the absolute value of secant x. And that's the final answer. Now, the mistake I've made is that I applied it, I wrote x instead of theta, so let me fix that real quick. I'm going to erase all the x's. And this is not the first time I make such mistake. So it's really important to keep track of the variables of your integration. Here I'm using it for theta. Meaning that I have one more step of replacing it with 5x. And let's check if that's correct. And that's correct. Let's continue. Problem number 3. We have another product of tangent and secant. We're going to do some basic hygiene here, so we'll do a quick substitution. Theta is equal to 4x, so d theta is equal to 4 dx, meaning dx is equal to 1/4 of d theta. Now, -5 comes out, and then 1/4 also comes out, so we have tangent to the power 5 of theta times secant to the power 6 of theta d theta. And now we're going to check this method, let's check back with the lecture. So we have even power of secant and odd power of tangent. And m is even, n is odd. That seems to be the last case, right? So the one at the bottom. When m is even and n is odd, so when the power of tangent is even and when the power of secant is odd, what we do is, I guess I haven't finished. Oh, that was fast. I feel like there's something missing here, right? I guess maybe we did that example earlier, but the idea is what? The idea is to use the trig identity, right? And the way we use the trig identity is that we simply we replace every tangent squared with the secant squared x minus 1. Every secant squared, seems like there's a typo here too. We have to have a secant cube over here, right? No, is it? Yeah, so this should be secant cube in the video, but that's the plan. We're going to use the trig identity and replace every hold on, no, I got it all flipped here. Let me rewrite this to match the pattern in the lecture. So secant goes first. Secant goes first, and this is important actually for you too to understand. The pattern described in the lecture uses secant first, and the n is the power of secant. So in our problem, secant is even, and tangent is, and regardless of what the power of tangent, we can use the first technique, which is split and substitute. So we're splitting away even secant, and here's what it looks like. Instead of secant to the power of 6, we're going to write secant to the power of 4 theta times tangent to the power of 5 theta, and we have like this secant theta squared here, d theta. And now we're going to do the substitution. The substitution is t is equal to tangent theta, meaning that dt is equal to secant squared theta d theta, which takes care of this. And now we just need to rewrite secant to the power of 4 as secant squared squared, so that secant squared theta can be replaced with 1 plus t squared using the Pythagorean identity. And now we have this. We have 1 plus t squared times t to the power of 5 dt is our new integral, which is just a polynomial of in terms of t. So we have to write it in standard form. So we're going to distribute everything. So we have here t to the power of 4 times t to the power of 5 is t to the power 9 plus 2t to the power 2 times t to the power 5 is t to the power 7 plus 1 times t to the 5 is t to the 5. So the antiderivative is negative 5/4 1/10 t to the 10 plus 2/8 t to the power 8 plus 1/6 t to the power 6 plus c. And instead of t, I'm now going to write tangent of theta, but theta is for x. So the final answer is negative 5/4 1/10 tangent to the power 10 of 4x plus 1/4 tangent to the power 8 of 4x plus 1/6 tangent to the power 6 of 4x and all that plus c. That's the final answer. Seems like the Newton actually used different pattern. Could have we noticed it ourselves? So if you look at this, we have secant is even. N is even. M is odd. Oh yeah, I guess, yeah, we could have, yeah. It satisfies both of these patterns, right? So we could have done either way. But I think problem number 1, we did it one way, and problem number 3, we did it another way. Okay, next one. So this is number 4, and here we are asked to use the reduction formula a few times, which is good. You should be able to apply the reduction formula, and the reduction formula tells us what. So I'm going to copy it over here. It says the integral of secant to the power n of x dx is equal to 1 over n minus 1 here we have tangent x times secant n minus 2 x plus n minus 2 n minus 1 integral of secant n minus 2 x dx. So this is the formula. We're going to set n equal to 5, and we're going to apply it. So 1/4 tangent x secant cube x plus n is 5, so n minus 2 is 3, so here we have 3/4 integral of secant cube x dx. But integral of secant cube x dx, here I'm going to use the power of technology, and instead of rewriting it, I'm just going to copy it. Instead of integral of secant cube x dx, I'm going to use the recursive formula again. So it's going to be, now I'm setting n equals to 3, and I'm writing everything inside of this parentheses. So when n equals 3, we have 1/2 tangent x secant x plus, here we have n is 3, so we have 1/2. And here we have an integral of secant, but when n is 3, n minus 2 is 1, so secant of x to the power n minus 2 is going to be just secant x dx. But we do know the integral of secant x dx, which is ln of the absolute value of secant x plus tangent x. So, picking the right answer, it looks like if we distribute everything, seems like the first one is the right one. And we finished the homework. So if you have any questions about integrating powers of secant, powers of tangent, and the products of powers of secant and tangent, please let me know.